This video demonstrates how to deduce a structure from a proton NMR spectrum. NMR interpretation is a complex subject, but this tutorial will get you started and will allow you to elucidate the structure of some simple molecules.
First, you must be given the molecular formula so you know how many of each type of atom are present.
Second, you will count the number of different signals and their relative integrations to see how many different sets of equivalent hydrogen atoms are in a molecule, and how many of each set are present.
Then, you will compare the chemical shifts of each signal to the table in your book or ebook to identify what functional groups are present.
Finally, you will use the signal splittings to determine which hydrogen atoms are adjacent to each other.
Now, let's work on an example so we can cover each one of the features of NMR spectra. Our example will be this spectrum for a compound with the molecular formula C2H6O. According to the molecular formula, this compound has 2 carbons, 6 hydrogens, and 1 oxygen. Only hydrogens give signals in proton NMR, so the fact that we see 3 groups of signals indicates that we have 3 different kinds of hydrogens.
In the spectrum, the integration is given as the red numbers in the parentheses. For the group of signals around 1.3 ppm, the integration is 3. That means that there are 3 hydrogens in that molecule that give rise to that signal. The small signal around 2.6 ppm has an integration of 1, which means that this is a signal that is being generated by 1 hydrogen.
The group of signals around 3.7 ppm has an integration of 2, which corresponds to 2 hydrogens. So now we know that there are 3 groups of hydrogens in the molecule. One group has 3 equivalent hydrogens, one group has 2 equivalent hydrogens, and there is 1 single hydrogen as well.
The integration is not always given in numerical form. Sometimes you will see integral signs superimposed to each signal, such as in this example. The area under the NMR resonance is proportional to the number of hydrogens which that resonance represents.
You can measure the integral signals using a ruler and figure out what is the proportional relationship between them. Notice that integration only gives information on the relative number of different hydrogens, not the absolute number.
Now, let's look at the table and determine what information can be gathered from the chemical shifts.
The single hydrogen on our spectrum might be directly bonded to oxygen, since the value for H on oxygen is between 1 to 4 ppm. If this is the case, then we have an alcohol as our functional group in this molecule, and it would have to be the spectrum of ethanol. As you can see, ethanol has a group of 3 hydrogens, the methyl group, and a group of 2 hydrogens, the methylene group.
It is important to understand trends of chemical shift in terms of NMR interpretation. The proton NMR chemical shift is affected by nearness to electron-negative atoms, oxygen, nitrogen, halogen, and unsaturated groups, carbon double bonded to carbon, and carbon double bonded to oxygen, and aromatic. Electron-negative groups move to the downfield, which is to the left, and results in an increase in ppm. In our case, the CH2 group is closer to the oxygen directly attached to it, so its signals are shifted to the left.
Now it is time to discuss the splitting of the signals. For this, we will use what is known as the N+1 rule. In general, NMR resonance will be split into N+1 peaks, where the N equals the number of hydrogens on the adjacent atom or atoms. If there are no hydrogens on the adjacent atoms, then the resonance will remain a single peak, a singlet. If there is 1 hydrogen on the adjacent atoms, the resonance will be split into 2 peaks of equal size, a doublet. 2 hydrogens on the adjacent atoms will split the resonance into 3 peaks, a triplet. If there are 3 hydrogens on the adjacent atoms, the resonance will be split into 4 peaks, a quartet.
Protons subject to hydrogen bonding such as the proton on the OH group of ethanol, will not cause the signals of neighboring hydrogens to split. For that reason, in our spectrum, we observe the following splitting pattern. Our spectrum has a singlet around 2.7 ppm. This corresponds to the OH hydrogen, and a triplet around the 1.3 ppm. This corresponds to the 3 hydrogens in the methyl group. The signal is split into a triplet due to the neighboring 2 hydrogens in the methylene group, and a quartet around 3.7 ppm. This corresponds to the methylene hydrogens, and the signal is split into a quartet by the neighboring 3 hydrogens in the methyl group.